Right. So, yeah, like I said, I am Noah, and I'm be talking today about sort of climate physics, and specifically trying to tell a little bit of a story about how, understanding physics can really help us to, inform green policies going forward and figure out how to ask the best questions with the knowledge of physics. So, essentially the outline of what I'll be talking about today is sort of first starting off with just an introduction to sort of my path that sort of led me to doing a physics PhD here at Boulder, and then sort of getting more into the physicsy parts of the talk. We're going to be talking about the basics of the greenhouse effect, and then how to actually make a climate model, a little tutorial there, and then sort of moving a little bit past the physics into a bit more of sort of how physics can actually help to sort of inform policies, for example. And then we'll be sort of tying off, as is tradition here at CU Prime, with me describing sort of what my day is like as a physicist here. So we start off with my path to physics here. So I guess I was sort of homeschooled up until about middle school, and then in middle school I started really getting into things like robotics, very STEMmy. Here's me in middle school, and then in high school I switched to FIRST robotics and did that there, and this was one of my many sort of STEM interests. I was also really into chess, which isn't necessarily STEM per se, but it was another one of my big hobbies. Here's my high school chess team at the national sort of meet. I was also a mathlete in high school. So this is sort of, the picture there. And sort of as I was graduating high school, I applied almost exclusively to engineering programs, actually, except for one university where I applied to a program which was engineering physics, which I didn't know the difference at the time. But it turns out engineering physics is not like other engineering degrees. It ends up being more physics with a lot of freedom to do the engineering that interests you. So I went to Santa Clara University, which is like a mid-sized liberal arts university in San Jose, California, the Bay Area. And while I was there studying engineering physics and math, I was able to get some internships and do some research. I did a summer at NASA where I did some research on sort of 3D printing in space and sort of how to model the structures that you could build in such a system. And then I did further research while at Santa Clara in sort of fluid dynamics stuff. And so when I was applying to grad schools, I sort of knew I didn't really want to stick with fluid dynamics, and I was more interested in more of quantum-y things. So I ended up sort of pivoting off of these, but they were all very helpful experiences. Sort of today, I am I have interests outside of physics as well. I'm a big board game guy, so I play a lot of board games, some that are very fun and simple, and as pictured here, more pieces involved. I also, Colorado, I got a hike. Here I am, sort of in the background here. I think this is on a snowshoeing expedition, which was very fun. And also my COVID hobby was learning to solve Rubik's Cube. So that's something that I sort of still keeps my hands occupied to this day. So at Boulder here, I actually work for this guy, Josh Coombs, over in electrical engineering. So, I'm actually here, which means perhaps a second answer to, my path to physics is it's that. A short walk, about 5 minutes. And I sort of do research, like I said, in quantum now. I Googled quantum. This was one of the first image results. So I think, maybe a research question for me is how does this relate to my work? I'll maybe get back to you guys on that one. But yeah, so that's what I do. And it's not really related to greenhouse physics, as you can imagine. Although, in some ways it ends up having some crossover. But the work I'm presenting today is actually something that I did for my comprehensive exams here at CU. It's a little, different at CU versus at other universities, but most physics grad programs have these comprehensive exams in which you're expected to learn something that is sort of maybe not in exactly your research field, a little bit out of your wheelhouse. For me, climate physics was not quantum, so that got a pass. And then sort of present the ideas that you learned over the course of maybe 3-ish months, and then also have some sort of exam components as well. So this work is all stuff I did for my comprehensive exams. All right, so now let's get into the sort of meat and bones here. We're going to start by looking at sort of Earth here, and Earth is noticing that it's starting to get warmer, and so Earth dispatches its scientists to try to figure out how can we explain this sort of famous hockey stick graph, where the hockey stick sort of gradual changes, some changes, and then all of a sudden, post-industrial revolution, we sort of shoot up. So, Earth definitely needs to understand why this is happening, and hopefully what we can do to curtail at least the side effects of this change. All right. So we're actually going to start not with Earth, but several million miles away on the sun, because the sun is really where we get our warmth from here on Earth. It travels all that distance. So in the sun, specifically the center of the sun, we have lots of really dense, hot matter. In this case, let's say a lot of hydrogen atoms, so these protons. And because it's so dense and there's so much energy, they're sort of just jumping around all the time. And sometimes these atoms end up colliding, and at the energies of the sun, that can cause sort of this fusion reaction. And here, 4 hydrogens have sort of somehow converted themselves into 1 helium. And this process releases like a ridiculous amount of energy. So much energy that it has to escape the sun, both as heat and as light that we see here on Earth. So the temperature of the sun, at least the surface of the sun, ends up being this sort of very large number, which I have written in Kelvin here, but I guess in Celsius it's this plus 270 something. So very, very hot, much hotter than, for example, lava or magma, or most things that you would find on Earth outside of a laboratory. And this whole thing ends up producing this much power, 4 times 10 to the 26 watts. I guess, put this in perspective, we can think about the total amount of power that sort of all humans on Earth consume. They don't have any like ballpark guess for how many years we would have to sort of consume this power to get as much as the sun produces. Any like ballpark guesses, just random numbers?
Billion years.
Billion years? That's a good guess. It is unfortunately a little bit under. It's about 4 trillion years of the global human power consumption to get 1 second of what the sun produces. So this number is ridiculous, and lucky for us, only a very, very small amount of this actually makes its way all the way to Earth, some 8 light minutes away. So we don't, get instantly fried. All right, so this brings us to our first discussion question. So maybe just talk to someone you're sitting next to. We have 2 here, actually, I guess. The first one is, why do hot things glow? And then sort of a follow-up, how does the color of the glow of these sort of hot objects relate to their temperature? So maybe see if you can come up with any ideas. All right, maybe we'll come back again. Hopefully that was a little bit more time. So yeah, maybe now if anyone wants to share sort of what they were talking about and what sort of basic answers they maybe had to these questions. Yeah, sure.
Tyler had quite a thing slow, trying to stay in equilibrium with what's around. You've got a lot of energy, it goes out, some of it's not.
Yeah, absolutely.
The temperature, my initial thought was it's got to be the high energy, the gamma rays of that, but infrared is what we feel. What heats up my hand, what warmed up my house today. So I think the answer to that is probably around infrared is where it's maximum and deep drops on either side.
Okay, lots of good ideas there. Yeah, certainly some of that was right on the money. Yeah. Anything else? Yeah.
We talked about the idea of maybe there's sort of dipoles within a material, and when they're hot, they sort of jiggle, and that could make something.
Oh, yeah. Very E&M-y, yeah. Very that's a very good physicsy answer. Yeah, that's also a different way of approaching this, more of the electricity and magnetism versus the thermodynamics. But they both sort of are describing the same physics. So yeah, that's another great thing. So maybe what I would say to these questions is the basic idea of why hot things glow is essentially the hotter something is, the more energy it sort of has within it, and things would like to get down to lower energies typically. So it wants to release some energy, and it'll do that by heating up things around it, for example, and by giving off light. And so for the sun, space is pretty empty, so there's not too much around it that it can directly heat up. So it's got to reach a little bit further by emitting light, for example. And then sort of the color, how is the color related? Generally, the hotter something is, the higher energy it needs to give off. So you'll go from reds up to blue flames are higher temperature, but also sort of, as was mentioned here, most things that we interact with in day-to-day room temperature land, those are all in the infrared. So yeah, we are actually warmed by the air in here, which is maybe like 70 some degrees, 72 or something, is mostly infrared emission. So all ends of the spectrum are very important. For the sun, though, we're usually in this visible spectrum. All right. So the scientists on Earth here have figured out how to actually put on sort of solid scientific footing why hot things glow and how they glow. And that's described by something called Planck's law, one of the many things sort of named after this physicist. So Planck's law tells us that essentially the amount of light that comes off of something is related to its temperature. So here is our, I guess, 5800 is what this paper was using, Kelvin sun, and it produces this, what's called a spectrum, which is, this bottom axis is wavelength, but we can also think about that as color, okay? And sort of more simply, if you care about just the total amount of sort of light that a body gives off, it turns out that sort of F here is related to the fourth power of temperature. And that's sort of not at all obvious, but that's what the scientists on Earth have told us, and we can use that. So we're going to sort of put Earth back in here. And by the time all of the sun's radiation, makes its way to Earth, only about this much energy remains. Here, we've sort of divided by an area. So this is the amount of power, 350 watts, that hits every square meter of the Earth. So for reference, that's about, about half as much as a toaster requires when it's running. So, if you had a perfect solar panel, you'd maybe need about 2 square meters to power your toaster continuously forever. I will say, though, this is the number that's averaged over the whole Earth. So the sunny side of the Earth gets, more like double this, and the dark side of the Earth gets pretty close to none of this, okay? All right, so the scientists on Earth, they put up a telescope and they point it at the sun, and they expect to see this new thing that they find from sort of Planck's Planck's law. But when they actually look, they see this. They see dips and divots, and we're not actually getting all of that energy. And so this is the first sort of hint to the scientists that maybe somewhere between the sun and their telescope on ground, some of that light is being lost, and that'll end up being due to our atmosphere, which is the second key player after the sun in sort of global temperatures. So now the scientists on Earth want to determine what sort of the amount of energy that the Earth is getting from the sun at all times, sort of how much we have to play with. So here's that 350 watts per square meter that's coming from the sun that actually hits Earth. That'll go through the atmosphere. First, it'll pass through the ozone layer, which is sort of relatively near the top of the atmosphere. And the ozone layer does a great job of getting rid of some of that UV sort of very high energy radiation. So that sort of bounces back and leaves space, never making it down to ground level. Then the rest of the sunlight might travel through some clouds and eventually be absorbed by Earth. And only about 240 of those 350 watts per meter squared actually makes it down and gets absorbed by Earth. Okay? So then what happens is Earth absorbs this, gets a little bit warmer, but Earth must sort of glow itself. And in this case, the Earth is glowing infrared, not this visible light. So it's a much longer sort of form of radiation. And sort of throughout whatever processes happen in the atmosphere, Earth scientists put a satellite up in space that measures the infrared, and they see 240 watts per meter squared. So only 240 of these watts actually end up leaving the atmosphere. So we have two, questions here. One, how much does the Earth actually emit if 240 of it leaves? Is it all 240? Is it more than that, less than that? So here we're actually going to go back to, we're going to sort of look into this a little bit more carefully. So we know that the amount that is absorbed by the Earth, well, that's just some constant fraction of the amount that came into the top of the atmosphere. And that relationship is given by this sort of fancy T, which I'll be calling the transmission coefficient. So the amount of sunlight that makes its way through the atmosphere, that is transmitted through the atmosphere, is this, transmission of sunlight, T sub S. Similarly, the Earth light, only some of that will make its way out into outer space. So we have another transmission coefficient for Earth light. So to answer the first question, how much energy or how much light does the Earth give off? We can again appeal to Planck's law because we know the temperature of Earth, like 56 degrees Fahrenheit on average across day and night and the whole world. So we could sort of do that. Okay, we get 390 watts per meter squared. So that means that the sunlight, about 70% of sunlight makes its way down to Earth, but only about 62% of Earth light makes its way all the way out and leaves the atmosphere. So the rest of it is sort of getting trapped somehow. So let's go back to our second discussion question, which is sort of one, why does the amount of light that gets absorbed by the Earth have to equal, or maybe happen to equal, the amount that ends up exiting and going off into space? And then sort of a second question, why aren't the sunlight transmission coefficient and Earth light transmission coefficients the same? Because it's the same atmosphere that's going through, just in a different direction, right? So maybe we can take another 3 or 4 minutes and talk about that with your neighbor. Seems like it's sort of quieted down. Are we still going, or? Okay, cool. Well, I guess hopefully again you sort of got some good discussion out of that. But I guess maybe did anyone want to share what they were thinking about in terms of maybe this first question? Why the flux is the same going up and down? Yeah.
You just thought it was like some conservation of
energy. Yeah, that's almost exactly right. I mean, it is actually exactly right. It's conservation of energy. The thermodynamics people in the room, which I don't know necessarily that there are any, I certainly am not one, but they would say this is thermal equilibrium. If you can't have more energy going into a system than is leaving it. If that's happening, everything would heat up. And we notice the Earth doesn't continually heat up ad infinitum, it sort of goes through cycles. So we must expect that at least very close to the exact amount of energy that comes into Earth must leave the Earth for us to be in thermal equilibrium. Yeah.
Isn't the Earth cooling down, or is that like such a small effect that doesn't matter?
How do you mean? Like over time?
Yeah, like I feel like it started out as hot and molten.
Oh, okay, yeah. So over very different astronomical timescales, yeah. So that would be the thermal equilibrium of a much larger system than just the Earth-Sun system that is now trying to sort of meet a temperature. So I would say that that's more of a galactic scale.
That's like 240 versus 239.9.
Yeah. Something like that is probably right. Yeah, there's some sort of entropy that must be lost. So we probably are slowly cooling down on those sort of more galactic timescales. But that's not sort of in the human spectrum. Okay, so then I guess second question would be from some other group. What do we think about these transmission coefficients? Yeah.
That maybe they weren't equal because like the molecules in the atmosphere, like we know from quantum mechanics, that their energy levels are quantized. So it likes to maybe absorb the infrared light more than it does the incoming like ultraviolet light or whatnot. So it's easier for it to absorb the emitted light than the incoming light. So the coefficients are that.
Yeah, that's actually a very good answer, very right. I think we can think about this in terms of sort of quantum mechanics, like you said, with energy levels, meaning that certain amounts of energy differences are more easily absorbed. But yeah, essentially the mechanics that cause these transmission coefficients are different. For sunlight, it's mostly due actually to scattering. So light particles hit big particles and sort of scatter in all directions. That's actually why the sky is blue, for example, something called Rayleigh scattering. But then for the Earth light transmission coefficient, this is due more to absorption, which is sort of what you were talking about, where the molecules absorb and then eventually re-emit, and only half of that re-emitted light goes up, right? The other half is going to go back down. So there's sort of two different physics at play because the wavelengths or the energies of the two types of light are different. So we shouldn't necessarily expect that they actually have the same transmission coefficient. So that's exactly right. All right. So now we move on to the second point here, which is how can we actually make a model? So Earth again asks, how does the actual properties of our atmosphere affect these two transmission coefficients? And really what Earth actually wants is this. They want the climate model 2000 is what I'm calling it, which takes in an atmosphere and spits out sort of some global temperature, right? So I could say, what would happen if I doubled CO2 today? And it would say, nothing good. Yeah, so the key here, which sort of maybe was just mentioned, is molecular absorption is one of these key properties of this atmosphere that's going to matter. So the scientists on Earth, they shine light into these little canisters that are filled with their favorite greenhouse gas, maybe CO2. And then they sort of see what colors of light and sort of how much light ends up passing through, right? And sort of they can do this with really finely tuned detectors, and this ends up being like fancy lasers, and they can sort of figure out how much light each gas absorbs. And this is how we sort of begin to build this model. So you do this, you get shockingly complicated looking plots with all different lines, and this is sort of where quantum mechanics makes the most impact, is why these things aren't smooth and they're all jumpy and jaggedy. That's because of quantization, but we'll sort of push past this. And then sort of the scientists on Earth say, hey, but wait, maybe like altitude matters, because the temperature of the atmosphere changes as you go higher up. And so that is going to make making this model a little bit more complicated. And I guess actually like the amount of gases you have isn't like the same at all altitudes. So that, okay, maybe it's looking like it's going to get really complicated to model our whole atmosphere, because everything changes so much from the ground to the sort of top of it. So how do we actually do this? We're going to sort of borrow one of the most fundamental tools in physics, which is simplifying your problems as much as possible, and then building back your simple problem into solving the problem you wanted to in the first place. So this is how we're going to do it.
A question.
Yeah.
Blue line, is that spectrum of sun or the Earth radiation?
Yeah, this is the Earth.
Okay.
So yeah, CO2 taking out a good big chunk of the Earth's spectrum, for example. Same with water vapor. Great question. All right. So we are, how are we going to break this down? Let's imagine that this is the entire atmosphere, all like 11 kilometers of it. But we want to make the problem smaller. So we're going to split the atmosphere up into a bunch of small layers, maybe 11,000 of them or more. Maybe each of these is a 1 meter sort of tall chunk of atmosphere, okay? And then in every meter, we can figure out sort of how many molecules we have. And our goal is not to find the transmission coefficient of the whole thing, but rather to figure out how much of the sort of, I guess I've switched from F to I, from flux to intensity, but how much of the light that comes up through that atmosphere ends up remaining. And it turns out that some amount of that is going to be just transmitted. It didn't happen to bump into any of those molecules, so it just made it through no problem. And then also, some other chunk of it is going to be re-emitted, because these molecules have a temperature, so they also are going to emit light. Half of that goes up, half of it goes down. So the amount that makes it from height z to height z plus delta z, that's going to be the amount that's transmitted plus the amount that's re-emitted. And so now for probably the most sort of fancy looking equation here, the Schwarzschild equation is sort of what describes this. This says essentially this is the change in intensity over some height. In this case, this like 1 meter, for example. this little sigma here, I guess first, the sum is over all the molecules. This is a sum over H2O, CO2, O2, N2, anything that is in your atmosphere. So this sigma tells us how much a molecule absorbs, right? This N sort of says how many of those molecules are there in that little chunk. And then these other two things are essentially related to how much is transmitted plus how much is re-emitted. And I guess this is a minus, so technically this term has to do with absorption, not transmission, but they're sort of one minus each other. So that's the Schwarzschild equation. So this is essentially the physics that we are going to use to model the atmosphere. We just have to figure out all these numbers, which we do in a lab with lasers doing molecular sort of absorption. All right. So now we move on to the sort of final act here, which is how can we use this knowledge of physics to actually maybe stop some of this warming? So Earth, the Earth here, which I guess now we're going to move to an alternate Earth that is sort of enacting policies willy-nilly and perhaps not doing the best science, but they have the same information we do. They're going to ask sort of maybe this first question, which is, okay, if these greenhouse gases are causing these detrimental effects, maybe what molecules should we start restricting people from pumping into the atmosphere, right? And so if we look at the Schwarzschild equation, maybe one of the most enticing first points of this is just to say, we look at this term here, right, the absorption, we should restrict molecules that absorb a lot of infrared light because those seem to be the biggest culprits. And so if we sort of do that, we'd get some of these molecules. This is hydrochloric acid, hydrosulfuric acid, hydrofluoric acid. Kind of weird that they're all acids. I don't necessarily think of those as being greenhouse gases to begin with, but I guess that's what the science tells us. And so Earth Prime puts this law into place. You no longer can pump these into the atmosphere, or if you do so, you'll have to pay a fine or something. And they wait 5 years, and it doesn't seem like it works. Things are still getting warmer. Things aren't sort of working out as well. And so this sort of leaves their scientists puzzled. So they go back to the drawing board. But maybe they think now, hold on, why didn't that work? And it turns out that the reason that that didn't work is because those acids, they don't actually want to be acids for very long. So whenever they're in the atmosphere, they just interact with like oxygen and little bits of dust and everything in the atmosphere. They immediately try to become not acids. So they don't actually live very long in the atmosphere. So even though in the brief moment that they do live, they absorb a lot, over any sort of reasonable time span, they just sort of don't end up making much of a contribution. So the scientists in Earth Prime say maybe we need to factor in how long they live, right? So that's essentially pointing to this N term, right? The number of them has to sort of stay around long enough to have an effect. So this is the sort of metric they come up with. It's called the global warming potential, GWP. And it's essentially the total amount of absorption that 1 kilogram of gas on day one would have over the course of 100 years. So you start with 1 kilogram, maybe by the end you only have half a kilogram because half of it is decayed. But you kind of figure out the total amount it would absorb. And then they choose to sort of divide by the same metric for CO2. So that's sort of like everything is in relation to what CO2 is. Because as you'll see, CO2 is sort of the classic greenhouse gas. So like I said, focusing on number here. So they do this for various greenhouse gases. They find this global warming potential. CO2 is always one sort of by definition. And this is methane. It's about 23 times worse than CO2 for the same sort of amount of mass. Nitrous oxide, maybe 300 times. And then, oh boy, okay, we really jump up. These HFCs, hydrofluorocarbons, they end up being really bad, okay. And this is sulfur hexafluoride with a massive 22,000 times more absorptive, sort of more warming than CO2. So the policy number 2 is maybe take the top 10 on this list and say, we don't want to do those anymore, right? We no longer want to look at, we want to restrict the amount that we pump out of each of those. So I will say this is a very good metric, but unfortunately, after waiting 5 years, this is still kind of a failure. Policy 2 doesn't work. So I guess, could anyone maybe throw out a guess for what the scientists are missing? Because they made all this nice physics into this really helpful metric, but they're certainly missing something. Does anyone have any ideas? Yeah.
These guys.
Exactly. Yeah, they're restricting things that aren't being pumped into the atmosphere that much in the first place. Now, maybe it's still a good idea to have the restrictions in place for these, but if you sort of only deal with the edge cases and not sort of the biggest offenders, then you're not going to get very far. So here is actually, they think maybe we need to actually factor in how much is being emitted. And as you can see, this is actually a graph that has already been corrected for sort of, equivalent carbon dioxide. So, that 22,000 factor has already been put into this sulfur hexafluoride section. And really it's like, okay, clearly CO2, methane, and nitrous oxide make up, the vast majority of this emissions. So we need to make sure that any policy that we put in the future accounts for this. And so the metric of choice for physicists in climate science is something called radiative forcing, which is essentially just, remember that F number that we had before? It's how much does the change in CO2 from pre-industrial to today, today being 1998, of course, how much does that affect cause a change in that net flux? So this is very actually easy to relate to temperature. And so really we need to focus in on the top 2 or maybe top 3 of these and make sure our policies actually affect these top offenders. So I guess the last little bit of this talk, I'm going to talk on something that's very simple and, well, I guess maybe I shouldn't say that, is very helpful, which is to actually relate this radiative forcing to the thing we wanted in our climate model, which was change in temperature. And it's, like I said, a simple equation. It's just exactly a proportionality where lambda here is called the climate sensitivity, okay? And if we believed Planck's law from the beginning, you would get lambda equals 3.3 watts per degree Kelvin meter squared. It turns out that scientists on Earth, at least, observe 1.6 for this number. So that means that something other than just the physics we've described here is happening. And the question is, what is that? And it turns out that it's something called feedback mechanisms. So this is sort of more of an addendum to the talk, and this is something that's I find very interesting. So what's a feedback mechanism? It's essentially some mechanism by which the actual properties of the Earth change when temperatures start to increase. And these could result in so-called runaway warming, if, as things get warmer, these mechanisms want to continue making the Earth warmer, or they could lead to stabilization if these are so-called negative feedback loops. So I'm going to show you one of these, which is ice melt feedback. It's essentially the fact that when sunlight comes down and hits the Earth, and this is a spot that's very icy, ice is white to the eye. It's very reflective. So most of the sunlight that hits ice actually just bounces off, goes straight up, back out to space. So it doesn't get absorbed by Earth. So that's not part of that 240 sort of watts per meter squared in our budget. But of course, if ice melts, less of this is going to be bounced off and more of it's going to be absorbed either by the ocean or by the ground that the ice is on top of. And so if you remember this plot, which I sort of forgot to actually mention during the discussion question, this sort of shows that all of the icy regions of the world up here at the North Pole, they're actually getting, they're losing a lot more energy than they're gaining in terms of flux. And that's because they're just bouncing off all of the sunlight and not absorbing it. And so sort of the less icy parts of the world have to compensate by absorbing more than they get rid of, essentially. And then sort of, atmospheric currents and whatnot will hopefully make the temperature of the whole Earth more equilibrium. So this was an example of one feedback mechanism. I want to sort of bring us to our last discussion question and also sort of the end of the physics portion of this talk, which is just discuss with your neighbors, see if you can think about any other systems. I know this is maybe asking a lot since I've only given you one example that might cause feedback. So that means something that depends on temperature that will relate to the warming of either the amount of greenhouse gases or the warming of the Earth, okay? And then I guess try to think of all the ones you mentioned. Think if they are positive, meaning they want to like keep warming the Earth and go in this runaway greenhouse effect, or if they're negative, if they're going to have a cooling effect. So maybe give 2 or 3 minutes for that. We'll wrap up there. So I guess I'm sure I've heard lots of great things sort of happening in the audience here, but I guess does anyone want to share maybe some of the things that they think might be feedback mechanisms? Oh yeah.
So with the warming, you get an increased rate of evapotranspiration because we'll put more atmospheric water, like increase in atmospheric water, and then that's a greenhouse gas, so it'll be even more water going, so we get a positive feedback loop.
Yeah, absolutely. Water vapor feedback is perhaps the most important, at least the climate scientists think about today, the most important feedback effects. And did you say that was warming or cooling? Yeah, that's right. That's a positive feedback. Any other examples? Yeah, sure.
We were thinking about the climate change could either go or prevent the global circulating currents of oceans for people up to the surface.
Oh,
So
yeah.
depending on whether factor either positive.
Yeah, so this is sort of getting at this is absolutely a feedback mechanism that does exist. It has to do with something called the carbon cycle, which the ocean plays a very large part in. And I guess, did you think this would be warming or cooling? You sort of,
We weren't really sure.
yeah, it's sort of not obvious, but it actually this ends up being a cooling effect. So that's nice. Sort of, you have more convection, so you're sort of getting less carbon-rich water at the top of the ocean, and that makes the carbon cycle sort of go a little bit quicker. And so that means there's going to be a little bit less CO2, for example, in the atmosphere as a result of the oceans warming up. So that's one good thing that happens due to ocean warming. I guess I will sort of show a list of maybe just 6. This is the first one I mentioned. Sort of ice melting is a positive feedback. Water vapor, that's also a positive feedback. Melting permafrost, it turns out that underneath the ice, there's a lot of great gases that's trapped down there. So that can add some extra gases, especially methane. That's another example of a positive one. Negative one, this one, I think, shame on Wikipedia. I wouldn't call this a feedback effect. This is just the only thing that keeps us not a boiling, pile of metal. Yeah, plants, of course. If you have higher temperatures, you can promote more plant life in some regions. And then this is the carbon cycle that was mentioned. Some other ones, clouds, for example. Hotter it is, more clouds. That has net cooling effect, for example. Desertification, the hotter it gets, sort of promotes more desert environments. That ends up increasing the amount of CO2 in the air. But also sand is more reflective than dirt, so that has a cooling effect. These things get very complicated, but they're very interesting and usually very intuitive. So that actually brings me to the end of sort of all of the climate physics. And so now I'll sort of talk about a day in my life, okay? So like I said at the beginning, I actually research quantum systems, so I don't do sort of climate physics, although I find it very interesting. Mostly I do things with quantum measurements and some research in quantum error correction, but really I have a very broad research interest. And I do theoretical physics, so I don't sort of touch experiments. Here's, for example, one plot from a paper we posted to the archive yesterday, which has to do with error correction, but I just think they sort of look pretty. So that's sort of our physics art department. So I think, as I've seen many other people do, I'm going to do a bit of a flow chart here. One super nice thing about being a theoretical physicist is that I can, do work from home and not in the lab every day. So I have a lot of freedom to make my morning my own, make some coffee. I'm actually more of a tea person, sort of browse the archive, try to see what other people are up to, and then sort of come into the office sometime between 10 and 12, depending on sort of meetings or how productive I need to be on a given day. And then one thing that I try to do a lot is try to read and try to stay up to date with what people are doing. And then sort of my day is split off into many different types of days. Sometimes I'll have lots of meetings with collaborators. I collaborate with various experimentalists and theorists that sort of know lots of things that I don't know, and they can teach me and I can help teach them some bits that I know. Leads to a lot of very interesting work. But then sort of when I'm not meeting with collaborators as a theorist, I am typically either writing papers, so working on drafts, editing figures ad infinitum, or I am sort of actively doing research. And what that looks like for me, I end up being very pencil papery rather than very, computer simulation. So I typically will, do some calculation, typically by hand, for whatever research question is currently interesting me. But then I inevitably have to use a computer to, create plots to see if any of the behavior that I'm expecting actually comes out of it. Really sanity checks to make sure I haven't messed up my algebra, which happens all the time. So then from there, I'll typically either find an error and know I have to, go and redo that calculation or change it in some way, or I'll get some ideas for new ideas that I can calculate. Sort of this loop sort of continues as I do more calculations and then sort of try to visualize them. So that is essentially what the day in my life looks like. And so I think with that, that is the end of my talk. Yeah. So yeah, any questions? Yeah.
You say like you do calculations and then plot it. Does that actually take the course of a day, or does it take like long time?
Yeah, that's a great question. So I would say it very much so depends. Usually it depends with how far into a project I am. Typically near the start of a project, especially if it's something that I don't know a lot about, I'm sort of building foundations to actually try to get some sort of intuitive understanding of what I should expect. And so those calculations, sometimes they can take quite a while. I end up, by virtue of sort of working in quantum mechanics, I do a lot with linear algebra, and a lot of that you can do, conveniently by hand. It's not sort of ugly integrals that you need Mathematica to solve. So, it definitely ranges, but I would say the longest calculations I've ever done have probably been of order a day. The average one, though, is probably order 15 minutes, something like that. And that's just because a lot of the time, especially near the end of the project, you'll sort of be, oh yeah, what would happen if we change this small thing? Okay, let's see. And it's usually at that point you have a good intuition, so you can answer them much more quickly. Yeah, great question though. Anything else? Yeah.
You mentioned 5 years twice, failure and failure-ish. Was that 5 years worth of model time or 5 year actual?
Yeah, I mean, I suppose since this was happening at on Earth Prime, not on Earth, I can answer this either way. So let's, I guess, maybe I can use this as an excuse to sort of talk about why modeling into the future is really hard, and climate physicists typically actually model from the past to the present. And that's just because of data, of course, but it's really because no one really understands the feedback mechanisms. And so looking further and further forward ends up being really hard. So if we had the perfect sort of climate model 2000 that could do all of these things, we could just like today see if I put this policy in place, what would the Earth look like in 100 years? And you could just see, but we don't have that. So really on Earth today, we are often doing the let's try something and wait a couple years and see how it works, which is unfortunate, but it's sort of the system that we have to deal with. So we have to try to figure out how to make the best of it. And that comes down a lot to, getting really good predictions and getting insights from science. Yeah, great question.